There we go. Thank you.
Thanks, Jim. So Joy is a postdoc with me who's been working on climate change related to malaria and forest birds, funding that we received from the Climate Change Science Center, and we're very grateful to be involved in that. In addition to the ecologists, we've now added a couple of climatologists here, and that I think that's been a real important thing that the climate people over here have done is making sure that the ecologists and the climate people start talking to each other and collaborating on what these things, how climate change is going to affect the ecology. So today I'm going to sort of talk a little bit of, this is sort of the outline we're going to follow. I'm going to talk a little bit about the malaria system and the model that we've developed for that. We're going to talk a bit about 3 different climate change scenarios that we evaluated. There's not complete agreement in what's going to happen in the future, as I'm sure you're all aware. And then sort of what that means, and then kind of try to wrap things up. So we, through the graces of NSF and the Biocomplexity Project, we were able to develop a fairly comprehensive, what we think is a fairly comprehensive model of the malaria system in forest birds for the island of Hawaii, at least for the east side of Mauna Loa there. It has about 50 ordinary differential equations in it. I'm not going to show them to you. Again, I'm going to spare you that, but I'm going to try to at least give you some idea of how the model works. It's done on these 3 species of birds. We hope they represent other Hawaiian forest birds in the community. Basically, birds are hatched as susceptibles. They had, on the left there. If they get infected from an infectious mosquito, then they go to the infectious stage in the model. A lot of them die after that. The ones that manage to survive go to this recovered stage where they're immune, but they're also infectious. So during either of these stages, if a susceptible mosquito bites one of these birds, it has a high probability of becoming infected. Mosquitoes are driven by sort of a developmental larval egg laying and larval development cycle. Once they become infected, the mosquitoes then have to delay for some period of time while the parasite develops, and this is called the latent period. And when the parasite develops, then they're infectious and they can bite susceptible birds again. So the model sort of is driven by all this sort of the process of the way the system works and our knowledge about how different relationships and how they're quantified. The key things for climate is that temperature affects lots of components of the system. It affects the mosquito development cycle. It affects the plasmodium maturation rate. It affects the actual infection rate. And also rainfall has some implications too, both on mosquitoes and on larval mosquitoes as well. So that's the key link, I think, between climate change and the model. And again, this is a model. We think it's a pretty good one, but obviously it's going to have limitations. In order to kind of predict what may happen as climate changes, we use the biocomplexity sites that I showed you before. 3 at low elevation, 4 at mid elevation this time instead of 5, and 2 at high elevation. And we use these as basically our baseline sources of data to drive the model. So there's some key pieces of that which I think I at least need to describe to you. One is temperature, average annual temperature. I guess the first is that we've broken this down into 3 different elevational gradients, and high elevation and mid elevation, and roughly in those ranges. I think we certainly appreciate that there are native birds above 1,700 meters. We haven't worked at that, and we could give some educated guesses probably from what the model's doing, but that's not part of what we're considering at the moment. These are the average temperatures for the baseline data for those elevations. You can see that temperature is highly dependent on elevation, and these are the average annual rainfall events or amount of rainfall. These are the 2 things that are changed by the future climate scenarios, and I'll talk about those in a minute. But these are the baselines that then we use to project what's going to happen forward. In addition, there are 3 other components that are kind of important to the mosquito cycle. One is these short-term dry periods, where we have periods of 5 days or so where we don't have much rain, and that's not so good on the larvae. It tends to dry out some of the larval habitat and have negative influences. And then actually when we have major rainfall events, that's not so good either for the mosquitoes. Good for us, good for the birds, not so good for the mosquitoes. Basically, it kills adults if it's heavy enough rainfall, and also then washes out larval cavities. A key component of this is the larval carrying capacity. So I sort of would look at this system as the drivers are climate, but the regulators are the larval carrying capacity. And the more larval carrying capacity we have due to things like pigs and what else, the more mosquitoes we can have, given everything else getting the same. So we average these values across from our study sites to use those as a way to project into the future what we think might happen. So today I'm going to talk about, I just showed you two sort of outputs from the modeling process we've been going through. Particularly, I think the key focus is on what's going to happen to the native birds. But also, I want to talk a little bit about what's going to happen to malaria transmission as we go into the future. Again, we really are focused on the eastern slopes of Mauna Loa. This may not apply very well to other places in Hawaii, like Kauai and those kind of things. Mosquito habitat may be quite different there. The dynamics may be quite different there. We're going to keep things confined to these three elevation ranges, and we're going to project things out to 2100, so about 100 years. And then we're going to look at three different climate scenarios. One is WRF. I think that's what my dog says when he's hungry. We'll talk about these in a second. One is RCP 45 and RCP 85. So three different, some way at least to bracket what may happen in the future in terms of climate. So the WRF model is one that's been developed by Kevin Hamilton's group here at the university. It's based on sort of dynamic principles, and I have no idea what coupled model intercomparison project is, but some of you probably know better than I do, but there it is. That's what it's based on. If you caught Oliver Tim's talk, he talked about these two other scenarios for climate change. The 4.5 is a fairly modest increase in CO2, and the 8.5 seems to be where we're headed now. It's kind of the worst, at this point, one of the worst case scenarios they considered. And Oliver's group, we've been heavily involved with Oliver's group trying to implement these on the landscape scale. They are downscaling these model projections through to a 3-kilometer grid, and then we are further sort of extrapolating those to a 1-kilometer grid, which is what our system is based on. There seems to be agreement between the models of what's going to happen with temperature up to 2100, but there seems to be quite a bit of difference between what they think is going to happen with rainfall. And as you'll see, that actually is potentially pretty important. In order to implement these, we basically assume that there's a linear change in the climate change parameters from now until 2100. Just to keep things simple, we're looking at the trends. So for temperature, the consensus is that high elevation temperatures are going to warm the most. Thank God, Hawaii is not going to warm as much as most of the mainland. I think we'd really be in trouble if we saw 6 and 8 degree increases in Hawaii. Less warming at middle elevations, and again, all the models seem to think this is pretty reasonable. And these pertain now to our study sites. They're not generic. So just so we're clear on that. There is a big disagreement in rainfall, and so I've lined these up as to 3 different scenarios. The wet scenario, which is the WRF model, predicts that things are basically just going to get wetter at all elevations in the future. The RCP 45 indicates that things are going to get drier. Potentially, they're going to get much drier in the dry season and less so in the wet season. And then the RCP 85 says things are just going to get even drier than that. So here's what sort of our model predictions of what we think may happen as these things progress. So this is for high elevations. This are Apapani, Iiwi, and Amakihi. As you can see, the Apapani, there's some decrease in populations at high elevations, but it's not really dramatic. They seem like they're going to probably be okay. If you look at all of these in general, you'll see there's actually some good news here. The good news is it looks like things are not going to change very much until about 2050 as things begin to we get sort of past some of that initial hump of warming. So that's actually kind of nice, but after that, things are going to get potentially a lot worse. And EV are the middle graph. As you can see, they're going down, and this is sort of our prediction of what's going to happen to EV. They're almost no matter which scenario you look at, EV are going to be in big trouble in higher elevation forests. Amakihi are going to have some issues as well. There's quite a population decline, but in this case, it depends a lot more on potentially what the future rainfall scenarios are. So, as I've already alluded to, there are significant differences for some of the species in terms of what may happen in the future. And we can, I guess, one of the several questions will come out of this. One is that what do we try to manage for? Do we try to manage for worst case scenario or what? And the other is then how do we get better knowledge about what's going to happen in the future so we can make a little better prediction about where things are going to go. At mid elevations, again, Apapani, yeah, they suffer a little bit, but not too bad. Again, the worst is for the WRF in red, and the best is for the RCP 85, the driest. EEV are already in big trouble at mid elevations, probably only being maintained by birds moving to lower elevation, I would guess in most cases. It's going to be completely grim for them, I think, at mid elevations. And Amakihi are not going to fare well at all either, again, according to sort of our best projections we can make. Okay, so the question is, why is it happening? Basically, as you might suspect, it's because malaria transmission is increasing as the temperature warms. So at high elevations, we're going from almost no transmission to fairly high annual transmission rates by 2100. Anywhere from sorry about that. Anywhere from maybe 20 or 30% to above 50% transmission at high elevations. Mid elevation is already fairly high. It's just going to basically hit 1. And low elevations, the annual rate is already high anyway. It's just can't go any higher than everybody getting infected, basically. So climate's not going to have much effect at low elevation than it is now. So the other thing we can do is break this down into the seasonal pattern of infection, and these show the daily probability of becoming infected, a bird becoming infected at high elevation, mid elevation, and low elevation. The key thing in here is that the major period when the action is occurring is during the dry season. Mrs. Cutter sort of pointed this out yesterday. That's when the temperatures are warmer, particularly at upper and middle elevations, and that's where the rainfall scenarios then become very important. And you can see the amount of rainfall that's being predicted in the future during the dry season can be a key driver of the infection rates. Not so much during the wet season when it's colder. Okay, so maybe trying to wrap some of this up. We think things are going to remain relatively constant, probably for the next 40 or 50 years, which is good news, I guess. And after that, infection rates should begin to increase, both at mid and high elevations. The weather climate predictions seem to make things worse. They increase they increase mosquitoes, basically. They increase infection rates. They negatively impact bird populations and increase our probability of extinction occurring. And it seems pretty clear we're going to lose, at least at these elevations we're looking at, maybe higher elevations, there will still be some refugia from disease, but it certainly looks like we're going to lose that high elevation refugia that we've had up until now. And I think sort of we would guess that probably there's a lot of other species out there, threatened and endangered other species that are probably at least as sensitive to malaria as the EV. So I think we need to think of the EV as a representative of sort of those group of birds as well. I think Lucas Fortini sort of talk about how the relationship between climate and bird distribution in the future sort of ties that together with this. So finally, I get to actually have a little bit of good news. And really, several studies I'm involved with seem to have nothing but bad news. So, but I think there is some good news, is we do have some time here before things are going to start to get worse, we think. However, I think it's really key that we get started on some of these things now, because some of the strategies, at least we're talking about, are not short-term. Things like reforestation, things like control of pigs are going to take a lot of effort into the future. And so we need to begin to think about those and plan for those and try to put them in place more quickly than waiting till the end. And I think any of these strategies we talk about really need to strongly take into account what's going to happen in the future as best we can predict that, and decide whether those strategies are actually feasible for providing long-term solutions or not in sort of a cost-benefit kind of approach. So this is the first phase of the climate change project that we've been involved with, is to look at sort of these long-term projections. The next phase for us is to actually begin to evaluate some of the potential mitigation strategies, such as pig control, such as sterile male mosquitoes, potential evolutionary adaptation and tolerance of some of the birds. We can at least evaluate that. We don't have any or very much control over it, or any that I'm aware of, but we can at least evaluate whether it could have an effect or not. So those are the two things that we've sort of agreed to do for our work. We hope also then to get to a third phase, which is where we actually sort of put this whole projection and potential mitigation strategy onto an actual real landscape on the east side of Mauna Loa, and talk about it over, how actually it might be implemented on a landscape scale and where things might change across the landscape. So I just wanted to acknowledge lots of folks who've already appeared before, but lots of our USGS collaborators and the climate people involved, and also to really thank the funders for allowing us to get involved in this stuff. There we go. Thank you. Thanks, Jim. So Joy is a postdoc with me who's been working on climate change related to malaria and forest birds, funding that we received from the Climate Change Science Center, and we're very grateful to be involved in that. In addition to the ecologists, we've now added a couple of climatologists here, and that, I think that's been a real important thing that the climate people over here have done, is making sure that the ecologists and the climate people start talking to each other. And then kind of try to wrap things up. So we, through the graces of NSF and the Biocomplexity Project, we were able to develop a fairly comprehensive, what we think is a fairly comprehensive model of the malaria system in forest birds for the island of Hawaii, at least for the east side of Mauna Loa there. It has about 50 ordinary differential equations in it, and I'm not going to show them to you. Again, I'm going to spare you that, but I'm going to try to at least give you some idea of how the model works. It's done on these 3 species of birds. We hope they represent other Hawaiian forest birds in the community. Basically, birds are hatched as susceptibles. They have, on the left there, if they get infected from an infectious mosquito, then they go to the infectious stage in the model. A lot of them die after that. The ones that manage to survive go to this recovered stage where they're immune, but they're also infectious. So during either of these stages, if a susceptible mosquito bites one another and collaborating on what these things, how climate change is going to affect the ecology. So today I'm going to sort of talk a little bit of, this is sort of the outline we're going to follow. I'm going to talk a little bit about the malaria system and the model that we've developed for that. We're going to talk a bit about 3 different climate change scenarios that we evaluated. There's not complete agreement in what's going to happen in the future, as I'm sure you're all aware. And then sort of what that, these birds, it has a high probability of becoming infected. Mosquitoes are driven by sort of a developmental larval egg laying and larval development cycle. Once they become infected, the mosquitoes then have to delay for some period of time while the parasite develops, and this is called the latent period. And when the parasite develops, then they're infectious and they can bite susceptible birds again. So the model sort of is driven by all this sort of way, the process of the way the system works, and our knowledge about how different relationships